What's up, guys? Josh Paul back here again, and today we're going to continue our discussion on intermolecular forces, right? And we're going to be focusing on periodic trends and the remaining intermolecular forces, right? So if you remember from the previous video, we focused primarily on London dispersion, right? We understand that London dispersion is in all molecules, right? Because all molecules are going to have electrons floating around in their orbitals. And therefore you're going to have dipoles that are being formed, and those dipoles are going to cause those attractive forces between those molecules, right? Remember, between means inter, right? So for today, we're going to continue along those plans of intermolecular forces. In the next video, we're going to do some practice problems. Alright guys, with no further ado, let's dive right into the lesson plan. Remember from the previous video of intermolecular forces, we primarily focused on London dispersion forces, right? And London dispersion, as a brief review, are just those attractive forces due to differences, or I should say due to electrons floating around in the orbital, and the probability that the electrons will be in the same environment or in the same region of the orbital, and that the adjacent molecule or the molecule next to it is going to have that same orientation, allowing for dipoles to form, allowing for attractive forces between those molecules. So let's go ahead and dive right into the lesson plan for today's video. Alright guys, so first up on the list, we're going to be going over periodic table trends. We're just going to do a quick review to make sure that we understand our concepts on valence electrons and other topics like that. Then we're going to dive right into dipole-dipole interaction, hydrogen bonding, and ionic bonding. So let's go ahead and start off with the periodic trends. So guys, as you can see on the screen, here's a table, the periodic table, and the periodic trends associated with the periodic table. So, for the most part, you don't really need to worry about atomic radius and metallic and non-metallic character. Well, I guess in the sense of metallic and non-metallic, that does play a role in terms of ionic bonding, but we'll cover that. The main part that you should be looking at is electron affinity, otherwise known as electronegativity, right? So we're going to go into further detail about what electronegativity actually means, right? When we say electronegativity, what are you visualizing, right? It's very important for you to be able to visualize electronegativity. Alright guys, so to simply put it, the definition of electronegativity is just simply how much an element or atom wants an electron, right? So we're going to go into why there is electronegativity differences, right? Why there are electronegativity differences when we're comparing one element on the periodic table versus another element on the periodic table. So go ahead, take a minute and think, right? We're going to take a minute and think as to why this occurs. So guys, if you remember earlier in the video, I mentioned the concept of valence electrons, right? So if you remember, valence electrons are the electrons in the outermost shell or the outermost orbital, right? Those are the electrons that are actually going to be partaking in the bonding that we are normally accustomed to seeing, right? So remember what valence electrons, right? Remember another concept we learned in Gen Chem called the octet rule, right? The octet rule implies that all elements want to be like the noble gases, right? So, say for instance, we're dealing with fluorine, right? Fluorine, we know, is all the way to the right of the periodic table, right? And has 7 valence electrons, right? So, if fluorine wants to be like a noble gas and complete its octet, is it going to be easier for fluorine to simply gain 1 electron and complete its octet with 8 valence electrons? Or is it going to be easier for fluorine to lose 7 valence electrons, right? Because remember, fluorine has the option to either become helium or to go up to its next noble gas, right? So that is the whole process of understanding why there are differences in electronegativity, right? So for something that is very far to the right hand side of the periodic table, right, that means it's going to have more valence electrons, which means it's only going to need one or two electrons to complete its octet. So it's going to be very stingy. It's going to be very greedy. It's going to be a bully. It's going to walk around saying, "This is my castle. I get this, that, and everything else," right? Whereas something that only has to lose one valence electron, like sodium, right? Sodium only has to lose one valence electron to complete its octet, right? Because it only has one valence electron in its outermost shell, right? So for something like sodium, it's going to be very willing to give up its electron, right? And remember, the definition of electronegativity is how bad an element wants an electron. So if something is willing to give up its electron, then it's not going to be very electronegative, right? And if something is willing to give up its electrons, right, electrons are negatively charged. Therefore, if you're giving up negative charges or negative vibes, you're becoming more positive. You can think of it in the sense of cutting out the negative people in your life and becoming more positive, right? And same thing as an electron, or I should say, same thing as the elements to the right hand side of the periodic table, right? If you're dealing with something like fluorine that's a very big bully and wants that extra electron, it's going to gain a negative charge because it's going to pull that electron closer to it. In some cases, it's actually going to completely steal that electron, right? And remember, when anytime you have a charge on one side of the atom, then you have, or molecule, then you have a charge, you should have a charge on the opposite side of the molecule, right? And therefore, that's going to cause the creation of dipoles. Remember, dipoles directly influence how we interpret intermolecular forces. So now let's take a look at the image on the left, right? If you look at the image on the left, we see that we have acetone, right? Just simply three carbons and a carbonyl group on the second carbon, right? So the way that I drew them, kind of like stacked on top of each other, is very important for the visualization part, right? So you see that double bond, right? Double bonds we know contain two bonds, and each of those two bonds are going to contain two electrons each, right? And typically, right, those electrons are, for the most part, we don't really visualize it, but for the most part, when we do, we put those electrons directly in the middle, right? Implying that there's a covalent bond, right? Implying that there's a sharing of the electrons. But in actuality, due to differences in electronegativity, as we just stated, if one element in the molecule is more electronegative than the other element in a molecule, say for instance oxygen, the oxygen that's double bonded to the carbon, if that's the case, then those electrons aren't going to be shared equally. They're going to be shared unequally, and this is what we call a polar covalent bond. Remember, polar covalent bond is an unequal sharing of electrons. So that's why on the image to the left, I brought those electrons a little bit closer up to the oxygen, right? Now, if we look over to the right, what do we know about electrons? They are negatively charged. If we're bringing something negative to the oxygen, it's going to get a partial negative charge, right? Therefore, the carbon is going to get a partial positive charge, right? And if we stack up another molecule like we did in the image to the left, right, and we stack them up in a fashion where they are head to tail, right, then we're going to see that the same thing is happening for the second oxygen element double bonded to the carbon atom, right? We're going to see a partial negative and a partial positive. And that green shade, right? Remember, these are large partial charges. Why? Because of the vast differences in electronegativity, right? The more electronegative an element is, the closer those electrons are going to be found to it, and the more negative that part of the molecule is going to be. Conversely, the more positive its counterpart will be. Right. So here we see a classic example of attractive forces due to differences in electronegativity. Now, if you remember, I recently just said that dipole-dipole interactions are a type of polar covalent bonding, which is unequal sharing of electrons, right? Now, hydrogen bonding technically is also a dipole-dipole interaction. It's just an extremely strong form of dipole-dipole interaction. Therefore, it gets its own category. Why? Because hydrogen is all the way to the left on the periodic table, and nitrogen, oxygen, and fluorine are all far to the right, and some of the most electronegative atoms we have in the periodic table. Therefore, the differences in electronegativity is going to be so vast, right, that these partial charges are going to be almost full charges, right? So they're going to be even larger than the charges that we experience in dipole-dipole interactions with the oxygen double bonded to the carbon, right? And hydrogen bonding, very important to remember, hydrogen bonding only occurs when hydrogen is directly bonded to nitrogen, oxygen, and fluorine. And down below, you can see a couple examples of different hydrogen bondings. Hydrogen bonding will be prevalent in any molecules that have an OH or alcohol. Amines are also prevalent. Carboxylic acids are going to have hydrogen bonding. And there are other cases as well. All right, now we are at ionic bonding, right? So what is ionic bonding? Ionic bonding is, for the most part, should be visualized as a metal bonded to a nonmetal, right? Remember, metals are all the way, typically, right, the main metals that we usually focus on, like sodium, potassium, lithium, those metals are all the way to the left of the periodic table, and we know from our periodic trends that they are going to be very low in electronegativity magnitude, right? The amount, how badly they want electrons, those elements, those metal elements, how bad those metal elements want electrons is going to be extremely low. Why? Because they typically will only have 1 or 2 valence electrons, so they'd much rather lose those 1 or 2 valence electrons than gain 6 to 7, right? So it is a complete transfer of the electrons because you have one element. Say, for instance, we are dealing with NaCl. Chlorine is so much more electronegative than sodium that it's going to completely pull its electron, the electrons in the bond, all the way to itself. So the chlorine is going to bring those electrons to itself. Therefore, once that happens, you're going to get a full negative charge being given to the fluorine, or I should say chlorine. I don't know if I unfortunately said fluorine or chlorine, but the principle still holds true because they are both halogens. Now, here's a little exercise to help you visualize what that actually means, right? So typically when we draw bonds, say for instance we're doing NaCl, so typically when we just say NaCl or any type of bond, we typically just draw that line, implying that those 2 electrons are being shared between each species contributing to the bond formation, right? But so let's go ahead and draw those 2 electrons in, and say for instance that those 2 electrons are in fact being shared equally, right? Now we can see that as we move from NaCl with a dashed line in between and NaCl with those 2 electrons in between, now we can see from our knowledge on electronegativity trends that chlorine is so much more electronegative that the electron from the sodium that's being donated by sodium is going to be completely transferred over to the chlorine, meaning that sodium lost a negative charge, therefore becomes positive, as you can see in blue, and then chlorine gained a negative charge. And remember, these charges are full charges that they're gaining and losing. Therefore, these full-on charges are not going to be partial charges. Therefore, you're going to have the strongest type of intermolecular forces. So we just covered in depth and went over the concepts and the basics and the foundations of what intermolecular forces are, how they impact us in terms of bonding, and how we can use periodic trends and knowledge of the electrons floating around the orbitals to actually visualize and see and understand what intermolecular forces are present when we look at a molecule. So without further ado, let's go ahead and go over to the problem set section of the website and complete the problem set for intermolecular forces.